In this video, we're going to be talking about how to create or how to insert nodes into a binary search tree. So before I start, let me remind you that binary search trees are a special case of binary tree that follow a very simple rule. The values on the left subtree are less than or equal to the value in the root, and the values on the right subtree are greater than or equal to the value in the root. So if we take a look at this, this is a typical binary search tree done with integers. So we see that the value at the root is 8. So all the values on the right sub 3, 10, 14, 13 are greater than the value of the root. And all the values on the left sub 3, 1, 3, 6, 4, and 7 are obviously less than the value that we have at the root. And any node that we pick, we can create a subtree and apply this rule recursively. So for example, if I take this subtree with the nodes 6, 4, and 7, the root is 6. And again, any value on the right sub 3 is greater than 6. Any value on the left sub 3 is less than 6. If I pick this node as the root, and therefore this is the subtree, then any value to the right of 10 is greater than or equal to 10, and we see that there is no values on the left sub 3. Because we're applying this rule, which is what makes a binary tree a binary search tree, we can say that the values are inserted in a sorted order with respect to the root node. In other words, if I were to trace a vertical line around the root node, which is 8, all the values to the right are greater than 8, all the values to the left are less than 8. If I trace a vertical line around any node, for example 14, all the values to the left of 14, which in this case are all the values that we have on the binary search tree, have to be less than. And to the right they are none because there is no values on the 3 which are greater than 14. So that's a very important rule to remember when we insert, when we remove, and when we search a binary search tree. So let's talk about inserting nodes on a binary search tree. Of course, the first step is going to be insert the root. So remember, we may be reading values from a file. We may ask the user to provide the values. So we really don't have control of how the values come in with respect to their order. But whatever the first value is, then we're going to store that at the root of the binary search tree. Once we do that, all the other incoming values, we need to choose the proper subtree, the right subtree or the left subtree, applying the rule that we just described. Of course, this process is done recursively, meaning that once you arrive to a node, then you decide whether you're going to go left or right based on the rules that we discussed at the beginning of the video. The important thing to realize is that you're going to see when we do a little demo that once you insert a node in a binary search tree, you never ever swap or relocate that node. That node stays what it is. So inserting values into a binary search tree is simply a matter of finding the right place for insertion. And to find the right place for insertion, we're going to follow the basic rules that we just discussed at the beginning of this tape. So let's see what happens when we try to insert values that are given to us in a random order into the binary search tree. And let's talk about the running times. So let's assume that we have this set of values in here. They're in random order: 50, 60, 40, 30, 20, 45, and 65. So the first step is to insert 50, and of course there is no questions being asked. It's the first value, the tree is empty, so it goes at the root. Okay, no need to compare with any other node. From now on, every value that is inserted, okay, the rest of the values that we need to insert, we need to start by comparing those values with the value at the root, and then make a decision whether we go to the right if the value is greater, or we go to the left if the value is less than 50. And then we're going to arrive to a new node, and we apply this rule recursively until we find a reference, a left child or a right child that is available. So let's try to insert 60. So we start here by comparing 50 and 60, and obviously 60 is greater than 50, so we're going to go to the right. And at this point, the right child of 50 is available. So we insert 60 as the right child of 50. The next value is 40. So we start at the root, and then we realize that that's less than 50, so we're going to go to the left. And at this point, the left child of 50 is available, so we insert 40 as the left child of 50. Next value is 30. We start at the root, right? And we compare that with 50 is less than, so we go to the left. Then here we have a new node, which is 40. And again, 30 is less than 40, so we go to the left of 40, and that happens to be available. So we insert 30 as the left child of 40. Let's insert one more, 20. So again, we start at the root. 20 is less than 50, we go to the left. 20 is less than 40, we go to the left. 20 is less than 30, we go to the left, and now we realize that the left child of 30 is available, so we insert 20 as the left child of 30. So notice that we have just been simply recursively, every time that we arrive to a node, applying the rule that says if it's greater, you go to the right, if it's less than, you go to the left. And notice that if we take a look at this binary search tree, all the values on the left sub 3, 20, 30, 40 are less than 50. The values on the right sub 3, only 60, is greater than 50. So let's try now to insert 45. So we start here, and 45 is less than 50, so we go to the left. And we arrive at this node, and we realize that this node is 40. We're trying to insert 45, so 45 is greater than 40. So now we go to the right of 40, and we notice that the right child is available. So the right thing to do is to insert 45. And finally, let's insert then 65, and then we start in the current tree, which is this one here. 65 is greater than 50, we move to the right. 65 is greater than 60, we move to the right, and we realize that the right child of 60 is available, so we insert 65. And this is the final binary search tree. Notice that when we inserted a node, we never have to move or swap the nodes that have been inserted. We simply sort of like cascade from top of the tree down the tree, applying the rule recursively, trying to find for a place of insertion. And once we find either a left child or a right child that is available, that's where we insert the new value. So let's think about this for a little bit. The expected running time of this insertion, I claim, is log base of 2 of n. And why is that? Well, let's take here step 6, right? So we're trying to insert 65. So what do? We compare 65 with 50. And to find the place of insertion, now we make a decision that says if we're going to insert 65, it has to be on the right subtree. Cannot be on the left subtree because 65 is greater than 50. So what that means is I'm not going to have to visit all these nodes, 20, 40, 30, 45, and 20, to decide where to insert 65. Because I know that 65 is greater than 50, I'm going to ignore completely the left subtree. So I'm ignoring half of the data that I have. Assume that this is a real-life example. So what is likely to happen is that the left subtree and the right subtree are going to contain, hundreds of thousands of elements. So let's assume that I currently have 300,000 elements in my binary search tree. When I ask the question, do I go to the right, do I go to the left, and I get an answer, I immediately are eliminating half of these nodes, half of the possible places of insertion. So from 300,000, I go to 150,000, some sort of like dividing by 2. And this process is called log base 2 of n, okay, where n is the numbers of nodes that I need to have. So the process of insertion is very fast because at every node, I am eliminating half of the data when I answer the question, do I go to the right or do I go to the left subtree? So very, very efficient. So not only is fast in terms of insertion, but also the fact that I don't need to copy or I don't need to swap elements on the array, which is always costly. I have to do it on a binary tree. So much more efficient, as I said, than using an array. Of course, we cannot control what the order of the values that we're given. So something that is commonly done is as we insert values, the idea is also to keep the tree balanced. In a previous or different video, we discussed the concept of balance. In essence, a good way to understand what a balance is that the right subtree and the left subtree contain the same numbers of nodes. So for example, if we have on a left subtree, let's say 10,000 values, and on the right subtree we have 350 values, well, that's not a balanced tree. But if we have something like, let's say, 150,000 values on the left subtree and about 200,000 on the right subtree, that probably is going to be balanced. Again, I encourage you to watch a different video on binary search trees and binary trees to find a definition for a balanced tree. So the idea is that every so often after we insert, let's say, 100 or 50 nodes, we check whether or not the tree is balanced. And if the tree is not balanced, there are very well-known techniques, very well-known algorithms that can balance the tree. So the efficiency of the tree is only maintained if we are inserted into a balanced tree. And the reason for that also has to do with the height of a tree, which we discussed in the same video where we discussed balance. And then we realized that the minimum height, remember height is the longest distance from a node that is a leaf to the root of the tree. So in this case, taking a look at what I see here, right, I see that the height is going to be 3 because the lowest or deepest leaf is 20 and there is 1, 2, 3 links to get to 50, which happens to be the root. So I will say that the height is 3. So the minimum height for a balanced binary search tree for n numbers of nodes happens to be log 2 of n. And that guarantees that we're going to inspect a minimum numbers of nodes to make the decision of where to insert the new value. Again, we can control the order in which the values are given to us. So what happens if we have this scenario? You're given 50, 60, 65, 70, 80, 88, and 95. What is interesting about these values? Well, they are in increasing order. Every value that we try to insert is greater than the previous one. 65 is greater than the previous 2, 80 is greater than the previous 4, and 95 is greater than all of them. So what's going to happen? What is the shape of the binary search tree? Well, let's try to reason about it. 50, that goes on the root. It will be the same value that I have in here, 50, correct? And then 60 is the next value. So I'm going to go to the right because 60 is larger than 50, right? So I will have something like I have in here. Then 65. 65 is greater than 50, it's greater than 60. I continue to go to the right. So right now I have 50, 60, 65, and I always going to the right. What's going to happen if I try to insert 70? It's going to be the right child of 65. And 80 is the right child of 70. And 88 is the right child of 80. And 95 is the right child of 88. So I'm always and only going to the right. I'm always and only using the right child. So there is no left subtree at all because inserting these nodes in this order never requires using a left child of any node. Conclusion, this is a linked list that starts at 50 and ends up with 95. So this is not a binary search tree anymore. This is a linked list. So to insert, I sort of like have to go through all the nodes. So assume that we continue with this series of numbers where every number is greater than the previous one. And let's say that we have 1,000 numbers like that. So what's going to happen? Well, in order to insert a new value after inserting 1,000 of them, I'm going to have to inspect every single value and ask the question, is it greater than or less than? So if I want to insert one value after the previous 1,000, I'm going to have to ask that question 1,000 times. I'm going to have to go through 1,000 nodes to insert 1,001. Well, that's directly proportional to n, and that behaves like a linked list. This is very important for you to understand, and you should learn a lesson here. The lesson is that a binary search tree works, or all the advantages that we discuss about a binary search tree are applicable only if the binary search tree is balanced. So we need to make sure as we insert and as we delete nodes from a binary search tree that the tree remains balanced, because otherwise we could be looking at a linked list disguised as a binary search tree.